X in what they call the least residue system that solves this cubic polynomial with a large, with a prime squared modulus. Now, one thing to notice that if A is a solution, that means the same thing as this, 121 divides A to the fifth plus 10A plus 2. Now, I don't like it so much. I think it's a good idea to envelop this in parentheses, right? Otherwise, it's kind of a dangling looking thing. But notice that 11 is a divisor of 121. It's the only divisor, the only proper divisor of 121 other than 1. And so that implies that 11 divides the same object. It's just the transitivity, right? The transitivity of dividing, I guess, the divisor operator, whatever you want to call it. Divisibility is transitive, I guess is the way to say it. Okay? So this is very powerful, actually, because it cuts down the amount of work we have to do substantially. And y'all, again, if 121 is a divisor of this solution expression, since 11 divides 121, 11, this A would be a solution to this congruence also, okay? So a simple, let me just write it. Let's say if M divides N, and N divides, let's say, C. Okay, that implies that M divides C, right? That's really all we used here. Okay, it's transitive. If M divides this thing and then N divides that thing, that means M is going to be a factor of N, so that means M has to be a factor of C. Okay, now, so that means all we have to do is look for solutions to this, because another way of saying this is if A is not a solution, if this has no solutions, then this has no solutions. The thing we're looking for, if this has no solutions, then the bigger moduli has no solutions also, okay? So that's the contrapositive. Now, it doesn't take long to note that 3 to the fifth, you can check this fairly quickly. And there's some theory that tells you to look for divisors of 11 minus 1. But 3 to the fifth is congruent to 1 mod 11. Okay, that's because 11 divides, and again, you guys can check it just to keep the thing short. 3 to the fifth is what? 243. So 11 divides 243 minus 1. Okay, and again, a fairly easy arithmetic computation to verify. Okay, but that means that would make this a solution, right? Because just think if 1 is right here, okay, and then you would have 32 right here. In other words, you end up with 11 divides 33. Again, folks, I'm being kind of brief about this, but if 3 to the fifth is congruent to 1, you have a 1 right here. Then you have 10 times 3 is 30, and then you have 33, and 11 does divide 33. So, and also M is congruent to 0 mod 11, right? M is congruent to 0 mod 11, so 3 plus 11M is a general solution to this smaller modulus expression. And again, any solution to this would also have to be a solution to this, and that's why we're actually looking at the smaller moduli. It's a simple but very useful truth, okay? Now, so y'all, the rest of this is just, and I'll try to minimize the commentary here, we need to look at substituting 3 plus 11M into our original equation. Remember, our original equation is an integer to the fifth power plus 10 times the integer plus 2, and that's exactly what we're looking at right here. It's hard to keep it on the same, yeah, I guess it's on the same screen there, isn't it? Okay. Now, y'all, right here, again, I was running out of space, and so this part right here is, do I have room here? Hope so. 3 plus 11m. Just didn't have room. Raised to the 5th is equal to this, right, folks? And I just didn't have room to write the whole thing out, right, folks? So this, just this part right here is the binomial expansion applied just to this object right here. Now, the very cool thing about this, when you're looking at mod 121, do you see how right here, all of these terms are going to be, that's another big deal about this, why we're doing it this way. This is congruent to 0, mod 121. Mod 11 squared. Okay, but you see how it's the same right here. This is congruent to 0. All the way out. All the way out, all of these terms are congruent to 0. So that's why just this part of it, you're only left with 3 to the 5th, the first term. This part's not congruent to 121, and this part's not congruent to 121. So those are the only two parts. That's why this changed to congruence, right? Okay. So there we go, folks. And again, the rest of this is just putting it all together. Okay, so you have to still include these two parts right here, which is what this was. And so what we get is that the whole thing, and that this part would become just 32 because this would be 0, right? 10 times 3, this part's 0, so you have 32. That's where this 32 comes from. Okay? Now at this point, folks, all we did, we're going to go through the possibilities here would be m equals 0, 1, 2, 10, right? You check those are the 11 possible remainders when you divide by 11. Okay. Now when you check for m equals 0, you get 285, which is not congruent to 0 mod mod 121, and so that means 3 is not a solution. You see, 3 would not be a solution. Now we're trying for m equals 1, which would be 14, right? Now let's see here. I didn't complete this one either. But what you would get right here, 3 to the 5th, we've already seen that's congruent to 1, right? So I'll put a 1 here. This is plus 5 times 81, which is what, 405? Okay, and then times 11. Now you see these numbers are still pretty big, right? Now 110 plus 32 is 142, but that would be congruent. The sum of these two numbers would be congruent to 21. Again, you guys can check that. Now you're still wondering, what do we do? How do we manage this? Well, 405 is the biggest number, so let's hack it down mod 121. Okay, and when you divide 121 into 405, you get a remainder of 42. So what we have right here is 1 plus. You see, you can do this. That's the joy of modular arithmetic. Okay, this would be 42. Again, when you divide 121 into 405, you get a remainder of 42. The 11 is still there, and the 21 is still there. Now this is a computation that can be done fairly easily. What I got, if you add this all up, you get 484. This is equal to 484. But notice that is 4 times 121, right? So that is congruent to 0. And again, y'all, we are talking modulo 121 right here. So you see, that's what happened when we substituted a 1 right here. So what we get is 14 as a solution. That is 14 to the 5th plus 10 times 14. Plus 2 will be congruent to 0. We just showed it right up here, folks. And again, this would be a very difficult task to try to figure this out by hand. You know, you know that you're trying to pick from the numbers 1, 0, 1. It's easy to check 0, 1, and 2 probably, right? Maybe it's easy to check all the way up to, say, in the single digit. Maybe it's already at 5, you're getting to be large, right? As far as raising something to the 5th power. So it's tough just to guess and test on something like this. But what really helped us here tremendously was this very first idea here of all we have to do is check the square root of 121, which is 11, okay? And that's just based on basic, what do they call it, the transference or the transitivity of divisibility. It's the transitivity of divisibility. And then after we expand this object, we see most of the terms are just congruent to 0. You see 1, 2, 3, 4 of the terms are congruent to 0. So you're not left with much to check. But then you're still faced with a little bit of arithmetic even after all of that, you know. And so, but you do get to this stage where you get 0, and you show that m equals 1 is a parameter. M equals 1 generates 3 plus 11, which is 14 to the 5th. So the solution is certainly x equals 14. Now, that is one solution. And I will say right now that a lot of people that won't watch the whole video will just say something about this in the comments, and that's fine. That's their choice. But I didn't check any others. I just stopped after I got one. And I didn't try to say I found the only one. I think you can have as many as 5, right? Because this is a 5th degree polynomial. But I did find one at least, x equals 14. And I have no idea if there's any others. Okay, don't know. I don't know if we could check. I think. No, I think well, I don't know. I just don't know. Okay, but you could add x equals 14 is a solution, and of course you could add multiples of 121 plus 121m, right? If you want to. But as far as just in this set, 14 is a solution. And it's the only one I found. There's possibly, maybe there's 4 more. I don't know, because again, this is a 5th degree equation. Let me know what you think. I didn't feel like doing the extra work, but x equals 14 is a solution. And it says find n(x). Not necessarily unique. Okay.